So, in this video, we're going to talk about how carbon dioxide is transported in the blood, and then about some special circumstances with breathing, like what hyperventilation, hypoventilation mean, for example. So, carbon dioxide is also carried in the blood. It can be dissolved in the plasma, 77% is. It can be attached to hemoglobin on a different part than the red blood cells, and most of it can be dissolved in the plasma as something called a bicarbonate ion. Bicarbonate. So how it becomes bicarbonate is this picture here. So this is the blood. Carbon dioxide will go into the blood from the body cells because it's a waste product. And it will jump on an erythrocyte, combine with water, and then split to form, as you can see, your HCO3 negative. That's a bicarbonate ion. And then will also split at the same time to become just hydrogen ions. So then what happens is that bicarbonate ion leaves the red blood cell, and that's how most of the hydrogen or carbon dioxide is carried as a bicarbonate ion, as you see in step 3. Since bicarbonate is negatively charged, what also happens when this bicarbonate ion leaves is chloride goes in to take the place of that negative ion, so it's in balance. And this movement right here is called the chloride shift. Hydrogen ions. The more hydrogen ions, the more acidic. So as carbon dioxide is jumping onto red blood cells, the body becomes more acidic. And so that's good to remember for later. And on this picture down at the bottom, the carbon dioxide will eventually get to the lungs, but we can't exhale bicarbonate ions, so it has to convert back to its gaseous form. And it does that just the opposite of this. It goes back into the red blood cell, combines with water to form carbon dioxide gas, goes into the blood, and will leave, and this is into the alveoli, so we can exhale it. Also in this video, we're going to talk about hemoglobin and something called hemoglobin saturation. Hemoglobin attaches to red blood cells at the iron portions, and there's for every red blood cell, for every one blood cell, there's 4 spots for hemoglobin attached to iron. The carbon dioxide, right carbon dioxide here, is bound to the globin part, and hemoglobin also transports hydrogen ions like I showed in that other video. So 3 things hemoglobin carries. The cool thing is when things start binding to hemoglobin, it actually changes shape to make binding more easier or less easier in some instances. So that's good to keep in mind. So something called an oxygen hemoglobin saturation curve is something we're going to talk about next. And this is 4 here. Each hemoglobin molecule, like I said, can bind 4 oxygen molecules. I might have said it wrong in the last part, but that's correct. So for every protein called hemoglobin, it can bind 4 oxygen molecules. So the more oxygen that you have in your blood, the more that is attached to hemoglobin. I'll say that again. The more oxygen you have in your blood, the more is attached to hemoglobin. So saturation increases, meaning the amount attached to hemoglobin, as partial pressure of oxygen increases. And it creates this S-shaped curve called the oxygen hemoglobin saturation curve. And you can see at the beginning of the curve, it's a very steep increase, and you can see that reflected in the numbers. When you jump from a partial pressure of 20 to 40, it has a 40% increase in saturation. And compare that to a 20 millimeter increase here, 80 to 100, 80 to 100. It's only a 3% increase. So at the beginning, there's a bigger difference. Hyperbaric oxygen chambers is the word here, oxygen. So the saturation curve continued. So when we inhale oxygen and oxygen diffuses into our blood, at that point it's about 98% saturated. So a way to measure that is with the pulse oximeter. Okay, you put it on your finger. It tells you how saturated your blood is with oxygen. Your saturation can get 100%, but you'd have to usually submit yourself to higher amounts of pressure, like in a hyperbaric oxygen chamber. That's exactly what happens. Altitude sickness is when you go up higher in altitude and you have less pressure to push the oxygen into your lungs. So that's the answer here. Why is there a lower amount of oxygen in your blood? Because there's less pressure to push it in. And it can be very dangerous if you don't see the symptoms or it happens too quickly and your body doesn't adjust. But most of the time it causes headache, nausea. It can lead to swelling in the lungs and swelling into the brain. Okay, so like I said, when you bring that oxygen into your blood, 98% saturation at the lungs. Now get this, when your blood high in oxygen goes and drops off oxygen in the tissues of the body, after it drops off the oxygen, it's still about 75% saturated. So it only loses, remember one hemoglobin has 4 oxygen, it only loses one of those oxygens, really. Unless your body is really working hard, like during vigorous exercises, and then it drops a few more, 1 or 2 more. That reserve, that extra 3 oxygens up per hemoglobin is called the oxygen reserve and used in times that you really need it. A few things impact how well hemoglobin holds on to oxygen. And one of those is temperature. So hemoglobin holds 4 oxygens. And higher temperatures cause hemoglobin to want to lose more oxygen. And lower temperatures make hemoglobin hold on to the oxygen. So this is, the word is elevated. Elevated temperatures diminish hemoglobin's hold on oxygen. Another thing that can impact it is pH. Remember when we talked about carbon dioxide being carried in the plasma as a bicarbonate ion? When it becomes a bicarbonate ion, it also becomes a hydrogen or releases hydrogen ions. More hydrogen ions, more acidic. So therefore, something called the Bohr effect. The word B-O-H-R, Bohr effect. The more hydrogen ions there are, the more hemoglobin will release oxygen. So increased or decreased pH. I'm going to show you that image here. Let me see. Format, presenter view. Can you see it? So it's decreasing here. So the normal line's in purple. The red line is a lower pH. So that means that when carbon dioxide is being released into the blood, it releases more hydrogen ions, which makes it more acidic, which causes your hemoglobin to release more oxygen. And that's called the Bohr effect. The next effect we're going to talk about is called the Haldane effect. When oxygen is released, so hemoglobin has oxygen, when it starts releasing oxygen, hemoglobin changes shape. So a conformational change in hemoglobin. This change of shape of hemoglobin increases the amount of carbon dioxide that can bind because more oxygen is being released. What I just talked about, the movement of the affinity of oxygen for hemoglobin or hemoglobin for oxygen, that shift of that curve, the first examples, increased temperature, an increase in hydrogen ions is called a shift right. They decrease oxygen's affinity for hemoglobin, and a shift left increases hemoglobin's or oxygen's affinity for hemoglobin.